Cobalt is element number 27 between iron 26 and nickel 28, and like most elements, it's really quite interesting. It is a catalyst, it can be used in magnets, it is important in the batteries that we have in all our modern electronic equipment, and above all, it is associated with the colour blue. The element or its compounds has been known for a long time because it's been used for colouring glass. I found in my cupboard at home quite a nice glass jar, which everybody has told me is a 19th century Christmas tree light with a candle in it, though I'm sure some viewers will tell me it's something more boring, but I still think it's a Christmas tree light. And you can see it has got this glorious blue colour.
Did you buy it in the 19th century?
I can't remember when I bought it, but it was a long time ago. They add a small amount of cobalt into the melt when they're making the glass, and so you get isolated ions of cobalt which have this nice blue colour. Cobalt itself is a shiny metal if it's polished, and it's relatively dense, it's quite heavy to hold. It's used principally in alloys with other metals. It used to be used a lot in making magnets, though now you can get more powerful magnets using rare earths. Because cobalt is a so-called transition metal, the ions of cobalt, say cobalt 2+, that's cobalt with 2 electrons removed, is usually not naked. It will be coordinated by other compounds. For example, if you make it using water, you get 6 water molecules round the cobalt. So here you can see cobalt in the middle with 6 water molecules round it. Now you might ask, how can you form so many bonds? And the answer is that the interaction is partly electrostatic, the negative oxygen interacting with the positive cobalt. If you heat cobalt chloride, which is beautiful red-coloured crystals, to a high temperature, you can drive off the water and make a sort of purplish powder. We found a lovely, really old sample of anhydrous, without water, cobalt chloride in a bottle that's still sealed up with its original wrapping. We felt we really didn't have the heart to destroy this historic sample, to destroy the wrapping, so you'll have to look at it through the glass. We had another sample of anhydrous cobalt chloride where the bottle had split, so air and water could get in, and you can see it goes back to the pinkish colour. So we've got 2 demonstrations for you. The first one is to demonstrate how in solution you can remove the water and substitute it with chloride ions by using concentrated hydrochloric acid. We were so excited to do this that the first time we didn't do it very well. We had a test tube of cobalt chloride solution, nice sort of pinkish colour, and tried dropping in concentrated hydrochloric acid. But although you could see some changes of colour, the concentration of the acid was not enough. So we reversed it and dropped the pink solution into the colourless hydrochloric acid. So now we had a whole test tube of hydrochloric acid. And what we saw, and I hope you can, is that as the pink solution goes in, it goes bright blue. And the bright blue colour is due to cobalt ions with 4 chlorides ions. So it goes to cobalt Cl4 2-, going from cobalt 2+ to minus ions. And the striking thing is, of course, that it's a much darker colour, even though we're diluting it. If you drop the cobalt chloride into water, you see almost no colour because it's so dilute. So the reason why you get this very intense colour is because of the change of the shape of the atoms immediately around the cobalt, going from 6 around the cobalt to only 4. And this change of shape changes the quantum mechanical rules in which the electrons interact with light. So in the second experiment, I want you to see what happens if you drop cobalt chloride solution into sodium hydroxide, quite concentrated, and you would expect to see a precipitate of cobalt hydroxide, which is pink. Now watch carefully. As it goes in, you get a precipitate, a solid, but it's bright blue. And then, as you watch, really quite slowly and satisfyingly, it gradually goes pink to make the product that you expect. So this is an example of a reaction where the starting material goes through some sort of intermediate compound and then makes the product. And it makes the intermediate very quickly, and then slowly it goes to the product. And what's happening is that, first of all, you get a mixed salt where you have both hydroxide and chloride, which is still insoluble, so it precipitates, and then slowly, and it's slow because it's in the solid state and has to redissolve, the chloride is replaced by hydroxide to give you the pink colour. And it's really quite mesmerising how these pink crystals rain down. Cobalt is also very important as a catalyst. It is used in a variety of industrial processes, particularly a process for converting natural gas, or rather a mixture of carbon monoxide and hydrogen, which can be made from natural gas and has the rather amusing name of syngas, for synthesis gas. And using a cobalt catalyst, you can then convert it to liquid fuels for cars or lorries. And the advantage is that you can take isolated gas fields where there's natural gas, methane, and convert it into liquid fuel that can then be transported. Cobalt is also very toxic. We had some powdered cobalt, so-called cobalt sponge, and Neil, our technician, was really quite nervous of this poisonous powder. But cobalt is also vital for life. It occurs in a molecule called vitamin B12, which is present in living organisms in rather a low concentration, but catalyzes a whole series of important biological reactions. And the structure of vitamin B12 was determined by the British chemist Dorothy Hodgkin, who was the only woman who's won the Nobel Prize for Chemistry from the UK. So it is really a very historic structure.
So this is Neil's new device. It's a very, very fancy erection. Essentially, we've used a laboratory stand and we have an eyelet. So this is just to act as a point with which we can raise up our cesium on a piece of string.